Our planet is a restless giant. Beneath its seemingly tranquil surface, a fiery heart beats. Volcanoes, these awe-inspiring portals to Earth's interior, remind us of the immense power that lies dormant within. Recently, a surge in volcanic activity across the globe has captured headlines and ignited concern. From the icy landscapes of Iceland to the tropical islands of Indonesia, volcanoes have roared back to life, spewing ash, gas, and lava. This heightened activity serves as a stark reminder of our planet's dynamic nature and the forces that shape it. These fiery giants, once relegated to the realm of myth and legend, are now at the forefront of scientific inquiry. Researchers are working tirelessly to understand the causes and consequences of this increased volcanic activity. Their findings not only illuminate the inner workings of our planet, but also underscore the importance of preparedness and the need for effective disaster mitigation strategies. As we stand at the precipice of a new era of volcanic awareness, it is essential to educate ourselves about the science behind these awe-inspiring events. By understanding the forces that drive volcanic eruptions, we can better prepare for their potential impact and ensure the safety and well-being of communities living in the shadow of these fiery giants. The past few years have witnessed a dramatic increase in volcanic activity around the world. Iceland, known for its stunning glaciers and geothermal wonders, has experienced a surge in seismic activity, signaling the potential for major eruptions in the near future. In Italy, Mount Etna, Europe's largest and most active volcano, has erupted multiple times, disrupting air travel and blanketing nearby towns with ash. Indonesia, home to the infamous Krakatoa volcano, has also seen a resurgence in volcanic activity, with Mount Luotobi erupting multiple times and forcing the closure of several airports. Meanwhile, in Hawaii, Kilauea, one of the world's most active volcanoes, continues to erupt, spewing lava and creating mesmerizing displays of fiery fountains. These recent events serve as a stark reminder of the unpredictable nature of volcanoes and the very real threat they pose to human life and infrastructure. The Philippines, located along the Pacific Ring of Fire, has also experienced its share of volcanic unrest. The eruption of Taal volcano in 2020 caused widespread evacuations and disrupted air travel for weeks. These events highlight the global nature of volcanic activity and the interconnectedness of our planet's systems. Volcanoes are essentially vents or fissures in the Earth's crust that allow molten rock, ash, and gases to escape from the planet's interior. This molten rock, known as magma when it's beneath the surface and lava when it erupts, originates in the Earth's mantle, a layer of hot, partially molten rock that lies beneath the Earth's crust. The Earth's interior is incredibly hot, with temperatures reaching thousands of degrees Celsius. This intense heat is generated by a combination of factors, including the decay of radioactive isotopes, residual heat from the Earth's formation, and frictional heating caused by the movement of tectonic plates. The heat within the Earth's mantle causes the solid rock to behave like a very viscous fluid, slowly churning and convecting over millions of years. This convective motion within the mantle can cause magma to rise towards the Earth's surface. When magma reaches the surface, it can erupt, releasing pent-up pressure and spewing lava, ash, and gases into the atmosphere. The type of eruption and the materials ejected depend on a variety of factors, including the composition of the magma, the amount of gas it contains, and the structure of the volcano itself. The upward movement of magma is a complex process driven by several factors. One key factor is density. Magma is less dense than the surrounding solid rock, so it tends to rise towards the surface, much like a hot air balloon rising through the air. This buoyancy force is countered by the viscosity of the magma and the resistance of the surrounding rocks. Another important factor is pressure. As magma rises through the Earth's crust, the pressure on it decreases. This decrease in pressure can cause dissolved gases in the magma to come out of solution, forming bubbles. These bubbles can significantly increase the volume of the magma, making it even less dense and further driving its ascent. The composition of the magma also plays a crucial role in its eruptive behavior. Magma rich in silica, a common component of volcanic rocks, tends to be more viscous or resistant to flow. This high viscosity can trap gases within the magma, leading to more explosive eruptions. In contrast, magma with lower silica content is more fluid and allows gases to escape more easily, resulting in less explosive eruptions. Section 5. Shifting grounds, tectonic plates and volcanic unrest. The Earth's crust is not a solid, unbroken shell but is instead divided into several large pieces called tectonic plates. These plates are constantly moving, albeit very slowly, at rates of a few centimeters per year. Volcanic activity is often concentrated along the boundaries of these tectonic plates. At divergent plate boundaries, where plates move apart, magma from the mantle can rise more easily to the surface, creating new crust. The Mid-Atlantic Ridge, a vast undersea mountain range, is an example of a divergent plate boundary where volcanic activity is common. At convergent plate boundaries where plates collide, one plate may slide beneath the other in a process called subduction. This process can drag water and sediments down into the mantle, which can lower the melting point of the mantle rocks and generate magma. The Ring of Fire, a zone of intense volcanic and earthquake activity that encircles the Pacific Ocean, is largely associated with subduction zones. Section 6. From local to global, the far-reaching impact of eruptions. Volcanic eruptions can have profound and far-reaching consequences, impacting not only the immediate vicinity of the volcano, but also regional and global systems. On a local scale, volcanic eruptions can devastate communities with lava flows, pyroclastic flows, lahars, and ashfall. Lava flows, though relatively slow-moving, can incinerate everything in their path. Pyroclastic flows, fast-moving avalanches of hot gas, ash, and volcanic debris, can travel at speeds of up to 450 miles per hour, incinerating everything in their path. Lahars, mud flows composed of volcanic ash, rock fragments, and water, can be triggered by rainfall or the melting of snow and ice on the slopes of volcanoes. Lahars can travel long distances, burying entire towns and villages in their wake. Volcanic ash, composed of fine rock particles and volcanic glass, can pose significant hazards to human health and infrastructure. Ash can irritate the eyes and respiratory system, contaminate water supplies, disrupt transportation systems, and damage crops. Section 7. When the sky falls, air travel and volcanic ash. One of the most disruptive impacts of volcanic eruptions is their effect on air travel. Volcanic ash, when ingested by aircraft engines, can cause significant damage, leading to engine failure. The fine, abrasive particles in volcanic ash can erode engine components, while the high temperatures within the engine can cause ash particles to melt and adhere to engine parts, disrupting airflow and potentially causing engine stall. The 2010 eruption of Eyjafjallajökull in Iceland demonstrated the global reach of volcanic ash plumes and their ability to disrupt air travel on a massive scale. The eruption grounded thousands of flights across Europe for several weeks, causing widespread economic disruption and highlighting the vulnerability of our global transportation systems to volcanic events. Section 8. Preparing for the unpredictable. Mitigating volcanic risks. While we cannot prevent volcanic eruptions, we can take steps to mitigate their impact and protect human lives and property. Volcano monitoring and early warning systems are crucial for providing timely information to communities at risk. Scientists use a variety of techniques to monitor volcanoes, including seismic monitoring, ground deformation measurements, gas emissions monitoring, and thermal imaging. By analyzing data from these monitoring systems, scientists can detect changes in volcanic activity that may signal an impending eruption. This information is then relayed to emergency management officials and the public, allowing time for evacuations and other preparedness measures. Land use planning is another important tool for reducing volcanic risks. By avoiding development in areas prone to lava flows, pyroclastic flows, and lahars, we can minimize the potential for loss of life and property. Engineering solutions such as lava diversion barriers and lahar channels can also be used to redirect volcanic hazards away from populated areas. Section 9. A call to awareness. The importance of scientific monitoring. The recent surge in volcanic activity serves as a stark reminder of the powerful forces that shape our planet. It is a call to action for increased scientific monitoring, improved early warning systems, and greater public awareness of volcanic hazards. By investing in research, technology, and education, we can better understand, prepare for, and mitigate the risks posed by these awe-inspiring geological phenomena. Volcanoes, while potentially destructive, are also a source of wonder and inspiration. They remind us of the dynamism of our planet and the interconnectedness of Earth's systems. By studying volcanoes, we gain a deeper understanding of our planet's history, its present, and its future.